Recording.
So good morning and happy Monday to everyone. So today we're going to continue with linear equations with constant coefficients. And we're going to look at the, linear equations with constant coefficients. We're going to look at the non-homogeneous case. When I say non-homogeneous, I mean the ones that have non-zero on the right-hand side. And in particular, the method that we're going to explain is called method of undetermined coefficients. So first of all, I think it would be a good idea for us to review a little what we did last time. So here's what I would like to do. I would like to give you a bunch of equations, and I would like you to try to solve them. So x double prime minus 3x prime minus 5x is equal to 0. X double prime plus 2x prime plus 7x is equal to 0. And x double prime minus 10x prime plus 25x is equal to 0. Please go ahead and take a couple of minutes and solve these three equations by considering the auxiliary equation. Find the algebraic roots of the auxiliary equation, and then use them in order to come up with the general solution of the corresponding differential equation. Okay, and use variable t. Use variable independent variable t. Okay, please go ahead. Okay, so let's do them together now. So let's number them 1, 2, 3. And for the first one, I need to find the discriminant, which is going to be minus 3 squared, p squared minus 4 times 1 times negative 5, right? And this is 9 plus 20, which is 29. So we have two algebraic roots for the auxiliary equation. You know what? It might be a good idea for me to write the auxiliary equation so that everybody can see what I'm talking about. This is the auxiliary equation. And the two roots that I found would be 3 plus or minus square root of 29 divided by 2, right? And that makes the solution x of t is equal to c1 times the first one, so 3 plus square root of 29 divided by 2t plus c2 e to 3 minus square root of 29 over 2 times t, right? Are there any questions, please, for this first one? Let me do the second one. So again, let me write down the auxiliary equation, which would be r squared plus 2r plus 7 is equal to 0. What is delta here? Delta will be 2 squared minus 4 times 1 times 7, which is 4 minus 28, also known as negative 24, right? So this is less than 0, so we have two complex roots, which are going to be what? They're going to be minus 2 over 2 plus or minus square root of 24 over 2 times I. You can simplify it, obviously. So this will be minus I, minus 1. Plus or minus, now square root of 24, that's 2 square root of 6, right? So that will cancel with the giving you square root of 6 times I. And your solution is going to be x of t is equal to c1 times e to the negative t. Where do I get e to the negative t? By looking at negative 1, right? And cosine of square root of 6 times t plus c2 e to the negative t sine of square root of 6 times t. Questions, please. And let's do the last one. So here the auxiliary equation will be r squared minus 10r plus 25 is equal to 0. Here delta is 100, so 10 squared minus 4 times 1 times 25, which is equal to 0. So you have one double root, which will be minus negative 10, which is 10 divided by 2, also known as 5. So what is your solution? It's going to be C1 e to the 5t. That's the usual one. You would have expected to get that. And then you have that other solution, which is based on the fact that your auxiliary equation has a double root. And that's it. Okay. Questions, please. There is a nice interpretation that people like to give here sometimes. So remember that your double solution, your first solution is e to the RT, if R is your double root, right? That's the usual one. That's the one that you would expect to have anyway. So sometimes people, so that's the first one. Sometimes people like to think of the second one, if you want to have some sort of idea why in the world you get it like that, as the partial derivative with respect to r of e to the RT. It's a really wild suggestion to consider it like this, but the truth is that there is a theoretical basis to it, and that's the way sometimes people look at it this way. Not that you need to know that, but you know, it's one of those fun facts for these equations that have been studied very, very extensively. And these kind of equations actually occur in physics where? Can anybody tell me? Sometimes it's a good idea to keep track of where we find these equations, and actually the suggested textbook has some good material on them. But regardless, can anybody tell me where you find such equations in physics of the second order like this? Yeah, exactly. So study of oscillations. Okay, so this kind of equations of the second degree, in fact, the ones that have this kind of solutions, sometimes in physics, of course, you don't have the middle term, and the absence of the middle term simply means that you're going to have a just a sinusoidal curve. So just to give you an example, you would expect to see something like this. And here the auxiliary equation is r squared plus 9 is equal to 0. The two roots are plus or minus 3i. And eventually what you get is x of t is equal to c1 cosine of 3t plus c2 sine of 3t. And of course, the roots of the auxiliary equation are intimately connected to the frequency that you find for those solutions. So there's a very, very nice physical setup for this type of equations. And I would like to mention one more thing here. One more thing that the structure of these equations allows us usually to consider solutions over large intervals. In this case, of course, the solution is defined over the whole real line. And people have developed a very nice criterion for when the solutions are linearly independent, meaning when one is not a constant multiple of the other. So let me just write this here. So linearly independent solutions, at least for two of them. If you have three of them, then it's a little different. And of course, you may ask, why would I ever have three of them? And the answer is, if you had an equation of the third degree, then you would have seen three solutions. So linearly independent solutions for two means that one is not a constant multiple of the other. I just want to throw this fact out there. It's not like I'm going to use it so much, but you could check it at least for the ones that we have seen so far. So let's say that you have two solutions, y1 and y2, and you wonder, are they linearly independent? In most cases, this is obvious. I mean, you can see whether one function is a constant multiple of the other, but there is a very nice analytical property that we can describe here, and this is the so-called Wronskian determinant. So this is called the Wronskian determinant. Where you take a determinant which has pretty much the functions, and let me emphasize that this is a determinant that depends on t also, and their derivatives. And the funny thing is that in the setup that we're studying, y1 and y2 are linearly independent, if and only if their Wronskian is different from 0. And in fact, here there is a very surprising fact. It just suffices to be different from 0 for one point on the domain of definition, and then it will be different from 0 for every other point. Now, if you were to deal with three functions, then you would have needed first derivatives, second derivatives, and the functions first derivatives and second derivatives in order to come up with a 3 by 3 determinant. As I said before, I'm not going to pursue the use of Wronskian determinants in our course, but I think it's a good concept to at least have heard of. And I would like to come now to the main object of today's lecture, which is quite extended, and I would like everybody to be with me. Remember, of course, I keep telling you, if for no other reason, please be with me so that you can get your attendance. But now I really mean it, because it's a little bit. It has a few cases to consider here, and one needs to be careful. So, what am I talking about? Let me start with an example. Sometimes in these cases, it's good to give an example and see where it goes from there. So I start with an example. So let's say that you have a nice equation. So everything looks nice on the left. So y double prime minus 3y prime plus 2y. And so far, so good. It looks great. Everybody can solve it. And then instead of telling you that this equal to 0, we say that this equal to t. Oops. Now, in the physics context, usually that would come up in the case that you have you have a mechanical system. The mechanical system is described by what you have on the left, and then you have some external forces acting up there, and this is described by what you have on the right. So the fact that you have t instead of 0 makes this a non-homogeneous equation. A non-homogeneous equation. Okay, so this will be a non-homogeneous. And you have the corresponding homogeneous. So each non-homogeneous equation has the corresponding homogeneous equation, which is y minus 3y prime plus 2y is equal to 0. So you just replace the function that you have on the other side with the 0 function. Okay. So when somebody gives you a homogeneous equation, a non-homogeneous equation, the first thing that you always do is you find the solution of the corresponding homogeneous equation. So what would be the solution of the corresponding homogeneous equation? I believe we solved this equation on Friday. And please understand that none of the solutions of the homogeneous would ever satisfy the non-homogeneous. So we have to find something else. But interestingly enough, the thing that we need to find is not too far off. And I'm going to explain what I mean by that. So you can check your notes, or you can find the auxiliary equation, and that immediately will give you y of t is equal to c1 e to the t plus c2 e to the 2t, right? So that's the solution of the homogeneous equation using methods that we just discussed a moment ago, okay? Using just the auxiliary equation. So now, the point of this discussion is that the homogeneous equation and the non-homogeneous equation are very much connected to each other in terms of their solution. And here's how it works. So if, let me call it y star of t, is one solution. When I say one solution, I mean I'm not expecting any constant in it. So when y star of t is one solution, and sometimes people call it one spatial solution of the non-homogeneous equation, Then the sum of the general solution of the homogeneous plus the special solution of the non-homogeneous. So again, I repeat, this is the general solution of the homogeneous. And this is the special solution of the non-homogeneous. This thing put together, this expression put together, will actually form the general solution of the non-homogeneous. Okay, so you have to put this expression together, in other words. So you have to solve the homogeneous, find the general solution. You have somehow to find the special solution of the non-homogeneous. And our goal today is to show how to find that special solution. That's our work today. Okay, that's that. So we want to be able to leave the class today knowing how to find the general solution of the a special solution of the non-homogeneous, at least in some nice cases. At least in some nice cases. Okay, as you're going to see, it's not going to be, and we're not going to be able to find it in to find that solution in full generality, but we expect to find it in some cases. And I'm going to begin with this one that we have in front of us right now. So are there any questions, please? Before I show you how to find the equation, the special solution in this particular case. Are there any questions, please? Okay, then, so let me show you how to find that solution. So again, to keep track of what we were doing, the equation that I had was y double prime minus 3y prime plus 2y is equal to t. And the idea is simple. The idea is that you have to look at what you have on the other side and understand that this is a polynomial of the second degree, right? That's what it is. I'm sorry, of the first degree, not the second, of the first degree. So your expectation is that a polynomial of the first degree will be a solution of the non-homogeneous. And what you do is the following simple thing. You just arbitrarily prescribe it. So you say, what is the most general polynomial of the first degree that I can possibly have? And the answer is simple. It's at plus b, right? That's the most, so that's the most general polynomial of the first degree. So what you do is you say in the beginning, I have no clue what a and b should be, but if I plug it into my equation, maybe I will find out. To do so, you need the derivative of y, which will be a, and the second derivative, which will be 0. So if you plug everything in, you will get 0 minus 3a plus 2at plus b. That should be equal to t. Okay, let me pause and make sure that everybody's with me so far. Are there any questions? Okay, so how do you find this? The idea is pretty simple. You have one polynomial on the left, one polynomial on the right. The only way that two polynomials are equal is if they have the same coefficient. So what you do is you rewrite the polynomial on the left in a nice way with the terms lined up. So I have 2at plus b minus 3a. And basically the idea here is that I'm thinking of the polynomial on the other side as 1 times t plus 0. And now my claim is that this should be equal to 1, and this should be equal to 0. Did I mess up? Sorry about this. You're absolutely right. This should be a 2b. Thank you. To be or not to be, right? That's the question. Okay. So I set up my two equations. So I want 2a to be equal to 0, to 1, I'm sorry. And I want 2b minus 3a to be equal to 0. This can be solved quite easily. A is equal to 1/2. And 2b will be equal to 3/2. And eventually b is equal to 3/4. So what is my special solution? Let me call it y star or anything else you like for that matter. It's going to be 1/2 t plus 3/4. So now I can write the general solution of the non-homogeneous, so the general solution. So this will be y of t is c1 times e to the t plus c2 e to the 2t plus 1/2 t plus 3/4. And we're done. That's it. Okay. And that's the general plan for today. So the general plan will be to figure out how to prescribe correctly the expected special solution for the non-homogeneous. Okay, I repeat. We will always solve the homogeneous first, and then we will want to find a special solution of the non-homogeneous. Just one solution. Any solution will do. Okay, and we're going to describe here today what that solution should look like. Does anybody have any questions, please? So that's the plan for today. The challenge is how to prescribe, as you're going to see. This will become kind of interesting. I mean, it's not completely trivial. So it needs a little bit of work.
Yeah, quick question. Can you explain how 2a is equal to 1 more time? And like that part in both.
Yeah, so you have two polynomials on the two sides of that equation, this polynomial and this polynomial. And the only way that two polynomials are equal to each other is if they have the same coefficients for the same degree, for the corresponding degree terms. I remind you that you saw something like this when you had an argument of this type in what method that you have encountered in calculus? Does anybody remember where exactly you saw this kind of thinking? In partial fraction decomposition, right? In partial fraction decomposition, you clear denominators, you compared the numerators of the two expressions that you had, and you ended up with a situation like this. Okay. Any more questions, please? Okay, so let's begin by giving you one example to do yourselves, which will be of the same type. it will be of the same type. And then, so take a look at this, please. So y double prime minus 4y prime plus 4y is equal to t squared. Okay, so I claim that this is solved exactly the same way. You will need to rewrite this. I'm sorry, you will need to look, instead for a polynomial of the first degree, this will have to be a polynomial of the second degree. So you will have something like at squared plus bt plus c, but everything else will be the same as what we did before. So let me give you a couple of minutes, try to work this example out. Okay, please go ahead. Okay, so let's look at it together. So the auxiliary equation is rho squared minus 4r plus 4 is equal to 0. And the general solution of the homogeneous that you should have found should be C1 e to the 2t plus C2 t to the 2t, right? So far, so good. Everybody with me? Okay. Now let's find the solution of the non-homogeneous. How should we prescribe it? At squared plus bt plus c, which means that y star prime of t will be 2at plus b, and y star double prime. Actually, you know what? I'm thinking too much of functional analysis here. Let me put this as a subscript. Looks better. Like so. And this will be 2a, right? So now I plug them in, and I get what? I get 2a minus 4 times 2at plus b plus 4 times at squared plus bt plus c should be equal to t squared. Okay, let's line them up. Let's make sure that so you have all the t squares together. So that's 4at squared and then you have the t's together. Oh, oops, there is a t right here, right? Okay, and what are the t's? So we have a minus 8a from the second parenthesis or from the first parenthesis, and 4b plus 4b times t. And then the constants are what? They are 2a minus 4b plus 4c. And that should be equal to t squared. You might want to think of t squared as 1t squared plus 0t plus 0, which means that 4a should be equal to 1, minus 8a plus 4b should be equal to 0, and 2a minus 4b plus 4c should be equal to 0. So a is equal to 1/4. If you plug it into the second one, you will get minus 2 plus 4b is equal to 0, which means that b is equal to 1/2. And if you plug them into the first one, both of them, then you will get 1/2 minus 2 plus 4c is equal to 0, which means that 4c is equal to 3/2. And this means that c is equal to 3/8. So eventually we have that y star of t is equal to 1/4 t squared plus 1/2 t plus 3/8. And eventually we can write down the full solution, the general solution of the non-homogeneous, which will be c1 e to the 2t plus c2 t to the 2t plus 1/4 t squared plus 1/2 t plus 3/8. And that's it. Questions, please. Questions? Okay, I would like now to give you a couple more ways to prescribe some other things. So here's what it is. I will make a list. Okay, I will make a list. Here's how it goes. So here's what the right-hand side will look like. Right-hand side. And here's your prescribed solution of the non-homogeneous. And somebody might ask, do we have to learn this list by heart? And the answer is that this list is pretty much common sense. So there's nothing exotic about this list. So pretty much, if you have a polynomial of degree n, then the prescribed solution should also be the polynomial of the same degree. You know why I'm chuckling here? Because I'm lying. Yeah, I'm sorry, I'm lying. Okay. If I want to be more precise, I should say generically, which means that soon enough I'm going to tell you that the list that I'm giving you is true, except, and then I'm going to explain what the except is. But for the moment being, please take it as it is. Okay. Okay. So if you see a cosine of let's say 3t on the left, the idea is that you cannot just prescribe a cosine of 3t. You have to prescribe the whole thing. A of cosine of 3t plus b sine of 3t. That's how you should prescribe it. So the reason for that is when you play with cosines and you differentiate them, you always get sines, right? And that's why you need to pretty much use both of them. So if you had a sine of 5t, then what you should prescribe is a, again, cosine of 5t plus b sine of 5t. And if you see something like e to the negative t, what you should prescribe is simply a e to the negative t. And if you see e to the 3t cosine of 2t, it's the same principle as before. So you cannot just prescribe e to the 3t cosine of 2t times a. You need to prescribe a e to the 3t cosine of 2t plus b e to the 3t sine of 2t. And somebody might ask here the question, so what happens if I have an e to the 3t cosine of 2t and I prescribe just a e to the 3t cosine of 2t and I don't put the sign, right? What would happen? And the answer is simple. You will come up with a system that does not necessarily have a solution. Okay, so it will backfire if you try to get a shortcut here. Then let's say that you have a polynomial, and you're not going to see some crazy polynomial. So let's say that you have t squared e to the t. You just have to prescribe a generic polynomial like this, so same degree, times e to the t. Okay, or the same thing with cosine. So if you see a t cosine of 2t, again, you need a generic polynomial with cosine of the same degree, with cosine of 2t. And then, unfortunately, it's the same principle that I told you before, at plus b times, I'm sorry, not at plus b, other coefficient. So ct plus d times sine of 2t. So you can see that things can get pretty convoluted because look, when you prescribe, I doubt that I'll give you anything like that because the complexity of the algebra is unnecessarily overwhelming. So we pretty much, you start doing this and eventually you lose sight of what the problem was and you have some, very significant algebraic manipulation to do. But that's how it works. So if instead of t cosine of 2t, you had t squared, you would have needed two generic polynomials of the second degree. Okay, so far it's common sense. And here again, somebody might ask the question, why do I restrict myself to these functions? So why don't I give you, let's say, ln of t, right? Because there's no such easy prescription. That's the easy way to look at it. I'm giving you precisely things that can occur as solutions of the homogeneous equations, possibly multiplied by polynomials. That's what I'm giving you here. Okay? So that's the first table that you need, and pretty much the only table that you need to learn. And you don't need, like I said, you don't need to memorize it. It's common sense. If you see a polynomial, you keep the same degree and put all the coefficients, even if they're missing. If you have cosine, you will always have a sine in the mix and vice versa. And if you have exponentials, you will keep the same kind of exponential. Okay, it's as simple as that. Okay, so as one more example before we take our break, let's do the following. Let's do y double prime plus y prime plus y is equal to e to the t, let's say. Let's do this one. Let's try to solve this one, and then we can take our break. So what is the auxiliary equation here of the homogeneous? R squared plus R plus 1 is equal to 0. The solutions are, we solved this on Friday. I mean, it's no matter how you cut it, it's an easy equation to solve. Square root of 3 over 2 times I, right? That's the solution. And this means that the solution of the homogeneous is going to be C1 e to the negative 1/2 t cosine of square root of 3 over 2 times t plus C2 e to the negative 1/2 t sine of square root of 3 over 2 times t. And now, how should I prescribe my special solution? Very simple, just a e to the t. All the derivatives are the same. So the derivative of this is again a e to the t. The second derivative is still the same. And when you plug them in, you will get a e to the t plus a e to the t plus a e to the t. That has to be e to the t, which means that 3a e to the t has to be e to the t, which means that 3a has to be equal to 1, which means that a is equal to 1/3. So what is the solution eventually? It's going to be y of t is the solution of the homogeneous. Ooh, that's a long one. C1 e to the negative 1/2 t cosine of square root of 3 over 2 times t plus C2 e to the negative 1/2 t sine of square root of 3 over 2 times t plus 1/3 e to the t. And that's it. Okay? That's it. Questions, please. Okay, so please go ahead and take your break. Okay, welcome back, everyone. Are there any questions from the previous hour, please? Let's do one example with cosine. So why don't we solve y double prime minus y is equal to cosine t. Let's try to solve this one. Okay. And then I'll tell you how our story gets more interesting, possibly more twisted. But I think you're going to find it very interesting. Okay, let's do this together. This is quite simple. What do we have? We have r squared minus 1 is equal to 0, which means r is equal to 1 or -1. So the homogeneous, sometimes, I like to denote it like this. YH for the solution of the homogeneous is C1. Oops, why does it interpolate it like this? C1 e to the t plus C2 e to the -t. And now I want the special solution. So let me denote this by y sub s. Okay, that's another pretty good way of denoting things. So H for the homogeneous, S for the special solution. And what am I supposed to do? Take A cosine t plus B sine t. And what is its derivative? Its derivative is minus A sine t plus B cosine t. And the derivative, the second derivative, it's going to be minus A cosine t minus B sine t. So when I add them up, I get A cosine t, so I plug them in. I get minus A cosine t minus B sine t. That's the second derivative, right? Minus the function itself, A cosine t plus B sine t. That should be equal to cosine t. Now I'm gathering sines and cosines together, so that will give me minus 2A cosine t minus 2B sine t is equal to cosine t. Think of this cosine t as 1 times cosine t plus 0 times sine of t, And this should give you that minus 2a is equal to 1, and 2b should be equal to 0, which means that a is equal to -1/2, b is equal to 0. So the special solution I've been looking for is equal to -1/2 cosine t, right? And finally, I can tell you that the solution of the general solution of the non-homogeneous equation is going to be the solution of the homogeneous plus the solution of the special solution of the non-homogeneous. Okay, so general solution of the homogeneous, special solution of the non-homogeneous. Questions, please. Questions? Let's take our attendance with the keyword special, 30 seconds as usual. My apologies in advance to those of you who have stepped away. It can happen from time to time, but I think it's just the beginning after the break, so I hope everybody's here. Okay, so now here's where the part that I tell you that things are not always that simple. And in fact, I would like to illustrate. And this is how I'm going to illustrate it. Could you please try to solve the following one? Y double prime minus y prime is equal to 5. 5 is a polynomial of degree 0, right? So the generic polynomial of degree 0 is just a constant. So how would you solve this one? How would you solve this one? So your homogeneous would be r squared minus r is equal to 0. You have that r is 0 and 1, which means that the general solution of the homogeneous is going to be C1 e to the 0 t, I'm omitting that, plus C2 e to the t, right? And now you would say that the special solution, according to what we have said so far, would be just A. Why A? Because what is the generic polynomial of degree 0? And the answer is it's just a constant. Yeah, but then you have that ys prime is equal to 0 and ys double prime is equal to 0. And you will get 0 minus 0 is equal to 5. Good luck with that. Okay, there's nothing to be found here. So let me put 2 question marks here. Okay, let's do another one where things go wrong. Y double prime plus y prime is equal to 5 cosine t. Try to solve this one. Try to solve this one. Okay, let's see. Hamza, that's too late, right? I'm so sorry. I thought you were asking me now something about a lesson. So, what is, oops, sorry. I meant to say y. Sorry. I meant to say y double prime plus y. The one that I gave you with y prime is perfectly fine, actually. Y double prime plus y, that's the one I meant. Sorry about this. Okay, what would happen here? So again, you would have said r squared plus 1 is equal to 0, r is equal to plus or minus I. That would give you y of t is equal to y homogeneous of t. That would be C1 cosine t plus C2 sine t. And now the issue should become apparent, because what you're going to prescribe as spatial is a cosine t plus b sine t. But do you see already how this is this is absurd? You're never going to find anything that a and b, so that when you plug them in, you're going to get the same thing. Why not? Because this is essentially that. They're the same thing. So when you plug it in, you're going to get 0. Okay. So prescribing it as a cosine t plus b sine t simply doesn't work. Simply doesn't work. Okay. So what do we do? What do we do? There are some cases. In which the prescribed solution for the non-homogeneous as given in the previous table needs to be adjusted. the first thing that we need to understand is what is the general condition that prompts us to adjust? And the answer is as follows. Let's take the two examples that I gave you where our method breaks down. So when you look at the solution 5, I'm sorry, at the function 5, we said that so far on the right-hand side, we put only functions that could have been solutions of the homogeneous equation. The question is, what root of the auxiliary equation would have triggered the solution 5? And the answer is, if you have a constant solution, the implied algebraic root for what you have on the right is 0. Because when you have 0, you have the solution e to the 0t, or c1 e to the 0t, which is a constant. But this implied solution happens to be an actual solution of the algebraic one. Go to the next example. What would have been the solution that would have given you a cosine t? So what kind of solution of the auxiliary equation would have implied that you need cosine t? And the answer is I or negative I. You can take either one. So implied algebraic root is I. Yes, but I happens to be also a root of the auxiliary equation. So here's the rule. The right-hand side normally arises as possible solution of a homogeneous equation for a specific algebraic root. To make things simple, I'm going to call this root, the implied algebraic root. If the implied algebraic root on the right is an actual root of the auxiliary equation, then we need to adjust by multiplying the prescribed solution, so what you would have normally prescribed, by t in the case of a simple root, or t squared in case of a double root. It becomes more interesting when you consider equations of higher degree, but we will never do this here. Okay, so in other words, let's go back and correct our prescriptions here. Here, what we should have done is ys sub t should have been 80. So instead of a, you multiply by t. Why do you multiply by t? Because the implied algebraic root is the simple root of the auxiliary equation. And let's come to this one. The correct adjusted solution should be a cosine t plus b sine t, which is what you supposed, times t. And then if you plug this into your equation, you will see that it has a good amount of algebra, because you will have the product rule for derivatives, and especially when you go to the second derivatives. But eventually you will see that you have a solution. So let's do an example. So imagine that we have to solve y double prime is equal to t. Okay, imagine that you want to solve this. The truth is that this equation is so simple that you could solve it using calculus, but let's say that we don't want to do calculus at this point. So we have r squared is equal to 0. And so normally the equation, so that means r is 0 as a double root. So the homogeneous solution would have been c1 e to the 0t, which is 1, of course, plus c2 t to the 0t. So to make things easier, of course, I will write it as c1 plus c2t. Right? So that's the solution of the homogeneous. Normally, the special solution would have been prescribed to be at plus b, right? Because this is a polynomial of the first degree. But because of the coincidence that you have, you need to adjust. How do you adjust? By multiplying by t squared. Why t squared? Because I said in the previous rule that when it's a double root, you multiply by t squared. And here, of course, it's a double root. So this will give you at cubed plus bt squared. The first derivative will be 3at squared plus 2bt. And the second derivative, oops, not y, it says rather second derivative, is going to be 6at plus 2b. So pretty much if you plug it in, you will have 6at plus 2b is equal to t, which means that 6a should be equal to 1, 2b should be equal to 0, a should be equal to 1/6, and b should be equal to 0. So special solution, and now it's perfectly fine, is going to be 1/6 t cubed plus 0 t squared, so 1/6 t cubed. So the solution of the non-homogeneous, the general one, is c1t, c1 plus c2t plus 1/6 t cubed. And that's it. Okay. Questions, please. Let's do one more. So try to do y double prime minus 3y prime plus 2y, again, an example that we saw before, is equal to e to the t. I don't know, make it 5e to the t, why not? Okay, give it a try. Okay, the solution of the homogeneous, we have seen it before. It's C1 e to the t plus C2 e to the 2t. And you can see even the presence of this e to the t here tells you that you have a coincidence, right? So how do you prescribe the special solution? The special solution is what it would normally be, which is a e to the t, right? That's what it would normally be if you hadn't paid any attention to the left. But now that you did, this should be adjusted by multiplying by t. You see, it's not a t plus b. It's just what you had multiplied by t. And what is the derivative? The derivative is a e to the t plus ta e to the t. And the second derivative is a 2a e to the t plus t a to the t. So we plug them in and we get 2a e to the t plus ta e to the t minus a e to the t plus ta e to the t. There's a 3 here, plus 2 ta e to the t. And that should be equal to 5 e to the t. So now, look how nice everything is. Because you have ta e to the t plus 2ta to the t minus 3ta to the t, they cancel out, right? That's the beauty of this. And what remains is just minus a e to the t is equal to 5 e to the t, which means that minus a should be 5 and a is equal to negative 5. So the special solution is minus 5t e to the t. And we can give the solution of the non-homogeneous, which is C1 e to the t plus C2 e to the 2t minus 5t e to the t. And that's it. Okay? Okay. And okay, let me you mean in the homogeneous, if you have e to the 2t and t to the 3t. So if you didn't have this, right? If you didn't have that, then a to the t would have worked just fine. Yeah. It's only when there is a coincidence between what you have on the right-hand side and the solution of the homogeneous. That's really what it is. And I translated this to make it more precise. I translated this in terms of algebraic roots. Okay. So that will be all for today. The homework has been posted. Please do it very, very carefully. And we will certainly do a couple more examples next time from this. And then we will go on to something very, very interesting. You will see that we will stay on equations of the second order for a little bit. And we are going to look at some very, very interesting things going on here. And that will be all for today. Okay, hope, be well. Bye-bye.